Thanks, everyone. Yeah, my name is Johannes. I work at Argo National Lab. And the first things first, I acknowledge all the people that pay me and the people that paid the students that worked with me on this. So there's two co-authors here, Akilito and Stefan. They are two undergrad students that were paid by Google Summer of Code. Those two over there, exactly, that were paid by Google Summer of Code over the summer to work with me on the Attributor. And it was really great, and I'm really grateful for the funding. So what I'm talking about is the Attributor. It's like a framework to perform fixed point iteration. And I'm going to, let's dive into it. So, fixed point iteration, fixed point data flow analysis. Let's assume you have this like code. Well, you have a recursion, you have a function, and you're interested, what is the alignment of the return type? So what alignment does the return type have? That's your question. So what you could do is you look at the return type and you say, okay, the alignment of the return type is kind of derived from the alignment of the return values. So you look at P, which is the first return value you see, and you say, okay, what is the alignment of the return value P? And then you go further, okay, P is just the argument. You know the alignment of the argument. So, and you don't see all the call sites, so whatever is written there is all you know. So you know that the alignment is 16, you don't see all the call sites, that is where you stop. But the alignment of the return type is not determined only by that, but there's a second return. So there is the recursive call. So the alignment of the return type also depends on what the alignment of that return value is. What is that return value? Oh, it depends what the alignment of the return type is. And at this point, you realize, okay, now we have a problem. To answer the question we started out with, we actually have to answer the question we started out with. That happens not only in recursion, but it's basically a problem of loops. For me, recursion and loops, most of the time, it blurs together anyway. So if you want to ask questions about, if you want to answer questions about recursion or loops, you usually end up in this, circle. So what people did a long time ago, what they came out with is fixed point data flow analysis. So how does that work? We start out by pretending, we say, okay, for the first query, we say the return type alignment we assume for now is between 1 and infinity. So the only thing we know it's 1 for sure, because that's the lowest alignment that is possible, but we assume it's infinity for now, because we haven't found a reason why it shouldn't be. And then we go on and every time we initialize everything with this initial state that says it's between 1 and infinity. The return value, we don't know anything about it, so it's between 1 and infinity. But for the argument, we actually, we can't do that anymore because the argument, we don't know all the call sites, so we can only deal with what is there, and which is alignment 16. So we know the alignment is 16, and we have to, we also cannot assume more. We have found the reason why it's not more than 16. So we know it's 16 because it says so, and we have found a reason it's not more than 16 because, there is not, we can't look at all the call sites what input values are. So that the only thing we know is written there. And that is not sufficient, so now we go to query number, we use that information to backtrack and propagate it to query number 2, which totally depends on the argument, so it's 16, 16 as well. And then we go to call number 4, because we need 2 and 4, the results of both, to combine it to 1. We start with 1 infinity here, and then we go to, okay, what is the result for the recursive call? We already have a value for that, and that is between 1 and infinity. So we use that, propagate it back. Nothing changes anymore. The value is still somewhere between 1 and infinity. We combine those two. When you combine them, you take the minimum of the assumed values. So we know already that it cannot be more than 16. So the assumed value is capped at 16. We know that can't be higher. And we don't know we don't know that it's higher than 1, because for one of these inputs, it was just between 1 and infinity. So we get a lower and upper bound here, so we cap it. But now the trick is, because something changed for the blue value, we have to iterate again. We have to update it again and go through the whole system. So we start again here and use now the new blue value to update the green value, number 4, with 1 to 16. We combine those two. Still, nothing changed in blue anymore. Now, if we go over now, everything is now fixed. Nothing will change anymore. This is where it is. So actually, because nothing changes anymore, we can now move the known value to the assumed. So we can now say, okay, everything has alignment 16, which is true, and that is what we do conceptually in the Attributor all over the place. with a lot of things at the same time. Okay, abstract states. All works in like abstract states. In most abstract states we use are like assumed and known states. You don't have to design it that way, but that is how we like usually in all our attributes do it. So you have an assumed state, which was like the alignment, which it's the maximal alignment it could possibly be, and the known is what you already like can prove the minimal alignment it is. And then you iterate until you reach a fixed point state, where the assumed and the known alignment are the same, or the assumed and the known state are the same. It doesn't have to be integers, values, it's just like assumed and known meet. And then you have a fixed point and nothing can change anymore. Now, there's two special functions each abstract state has to provide, which is indicate pessimistic and indicate optimistic fixed point, which will force fixed points to happen. Either we set the assumed to the known value or the other way around. So what we did, like after nothing changed anymore, we could indicate an optimistic fixed point, the known values became the assumed values. And if we, for example, like time out, we have to do the opposite. We indicate a pessimistic fixed point, and we fall back to the known values at some point. Okay? Okay. Now, this was the example we just ran through, right? Just a quick reminder. We were interested in the return value alignment. That was our query. Let's see how you would do that with the attributor. What you would do is you would create an attributor, A. Then you would select what kind of information you're interested in. So there is this IR position returned function. Like function is our function we had. IR position returned is like an abstraction of what we're interested in, so the return value of that function. And then we say, attributor, get or create an abstract attribute with the type abstract attribute aligned for this position. So that is initially seeding the abstract attributes we're interested in. That's how you tell the attributor what it should derive information for, what kind of information and for what positions. And that is all you would do for this example. And then you would run the attributor. Then you would run the attributor, and it will run till a fixed point or timeout is reached, in which it like forces a pessimistic fixed point for you. And it will also manifest the information right now, but you could like split that apart if you want. Okay. In reality, if you would do this, you would actually get more than I showed initially in the example. If you want exactly what I've shown in the example, you would need to restrict it to alignment. Like you would say, all you're allowed to do is look at alignment information, basically. That is how you get what I've shown in the example, where only alignment was used to do any kind of reasoning. Because what is happening by default right now would be to allow liveness tracking and value simplification. Think sparse interprocedural constant propagation. So where you like pretend everything is dead initially. Based on that, you try to come up with constant values of things. Based on those constant values, you actually can argue that branches are actually dead or edges are dead, and so on and so forth. So that is happening under the hood. The alignment doesn't know that is happening. The alignment doesn't have to know. Like if you want it not to happen, you have to say like exclude it. But things are just like, the framework just does things for you. It gives you like better information if possible. Okay, so that is like a short summary. Now, what is the attributor? It is an easy way to introduce, like to run new fixed point analysis because it does a lot of things for you. It tracks dependencies, so it knows what to update and when, and what not to update. It has like a work list style algorithm, which is like fairly efficient. It has built-in timeouts and ways to handle what happens in a timeout. It is a powerful way to perform fixed point analysis because it allows you to look at things that are in flight, for example, liveness information. Like while you derive something, you can look at liveness information. And liveness information can look at what you're deriving. So everything that is in flight at the same time can be used in the fixed point analysis. Everything is interconnected. And then it is an alternative to inlining if you want. So interprocedural optimization with internalization, which we'll get to later probably, function rewriting is, function rewriting, for example, argument promotion, where you, instead of passing things by pointer, you pass it by value, actually can give you similar benefits to inlining. And we'll get to that at the end. Okay, so all these are good reasons, but why? Why did we sit down over the summer and build this? So what happened is, why do we need IPO in the first place, right? The short answer is inlining is limited. Right now, we had this IPO panel earlier, I'm not sure if you've been there. I said, like, inlining has limitations, and that is widely acknowledged. So we have to build, like, improve our IPO, because for now we usually try to rely on inlining, and our IPO is really bad. So what happens if you have recursion? Inlining doesn't work necessarily, except you like do tricks, which we don't. So that is out of the question. So, and if we handle recursion, we can basically handle loops. So whatever we build that handles recursion can handle loops in a decent way. So what we build there is not only good for recursion, but it's also good for loops. Then you have code size. If it's too big, the inliner will say no. But you still want to like transfer information and maybe code and other things between boundaries of functions. So like just giving up because something is too big or called inside a loop is not a good idea. Then parallelism. If you've been here last year, I gave a talk about how you can use inter-procedural optimization to improve performance of parallel programs. And in fact, that abstraction that I talked to you about there in that talk, that gets rid of all the overheads that parallelism introduces, like the function outlining, but the function outlining, the overhead that that introduces, is actually built into the attributor. Like if you write something in the attributor, you improve something, you write a new attribute deduction, it will actually work for parallel programs as well. It comes with a little caveat and a little extra cost you have to pay in terms of what to do and what you're not allowed to do or what you have to check, but you can easily opt out of this. But generally, it's like designed to work even in like parallel situations. And finally, if you have function declarations, or if you want to generate function declarations, you can use the information that we like derive, better information derive, to like annotate function declarations. We had a talk at the student research competition today about that. I hope you saw that. And you voted for it, obviously. But we'll also have a poster. I show it here, so tomorrow is the poster session. You should come there. Okay, so we have reasons not to do inter-procedural optimizations. We had the panel, we had reasons. Now, but what about a framework? Why did we build this attributor framework? Because we have function attribute deduction already, right? We could just improve on that. The thing is, I already mentioned, you can utilize information that is in flight in an optimistic state that you derive at the moment. And this is just a nice looking picture of part of the dependencies of the attributes we currently derive. So in the middle we have returned values, which derives the returned argument attribute, but it also captures all the values that are potentially returned at a function and where they are returned, through what return value. Because it has to gather that information anyway to add the returned argument attribute, it exposes that information. That thing uses the liveness information, which uses value simplification, which is like constant propagation and folding, constant folding, and so on and so forth, which in turn uses liveness information. These edges, the dotted edges, don't exist yet, but should exist. And a lot of things use return values. So this is just a nice looking graph to explain to you that there are dependencies between things, because the real graph looks like that. So we have more attributes and more dependencies between things, and it's for sure not the end. We can add more interconnected dependencies, reasonings, things like memory. If you can write or not write memory has an effect on capturing, has an effect on aliasing, has an effect on what kind of memory you're actually writing, has an effect on capturing, has an effect on aliasing, has an effect, and so on and so forth. So actually, it makes sense to put that all into a framework where the things can communicate with each other, can use information. To be fair, not everything we do needs necessarily to be in here, but the attributor is just because the fixed point iteration framework, it's just nice to live in there. So you can, you put it in there, and then maybe later you benefit from the fact that you can use the in-flight information, but you can also just use it as a fixed point iteration framework, a nice way to implement everything. Okay, so how is it designed? LLVM-IR positions, you've seen them earlier. We have, I think, 7 of them. Those are the 6 positions at which you can add an LLVM attribute. So that is, return values can have attributes, arguments can have attributes, functions can have attributes, call site arguments can have attributes, call sites can have attributes, call site return values. This is the call site return value here, right? It's the same thing. Can have attributes. And then we additionally have a floating position, which is anything else. Anything that doesn't fit the 6 categories is basically a floating position. So it could be a constant, a global variable, like any instruction, whatever you have. So it's just part of the framework because we like deduce through these positions. So you like say what position you want an information for, and then that is kind of the way you to do that. How do you, like, the core of everything is an update function. So the update function is, returns the change status, so it returns if the internal state changed or not. That is very important, and you have to always return changed if your internal state changed. If you don't do that, the results will be wrong. Like you will miscompile. You will derive wrong information. What it does is, like what you can do in a common pattern is take the internal state in the beginning, take the internal state at the end. If they're the same, nothing changed. If they're not the same, something has changed. That's a very easy way. Now, what do you do? Like this is value simplify returned update impl. So it's the update implementation of the value simplify for a function return value. Okay, so basically constant propagation, constant folding for a function return value. Like what is the function return value? It is basically whatever is returned, like you look at all the return instruction ret is all the return instruction, and you look at what the operand of them is, right? So to know what kind of, if you return always a constant, if all of the return instructions agree on what kind of value you return, that is the value return. Like if that is 5, all of them return 5, or the simplified version of them is 5, it's 5. Now, in the Attributor framework, you have all these check for all instructions, check for all called sites. You have like various of these checker routines, which take a predicate and then check things for you. And if you use them, you opt into liveness analyses and other things. Transparently, that is happening for you. So this will like call the predicate for all the return instructions, and a lot of things are cached in here. And then inside the predicate, what you do is you recurse. You ask for the value simplify result, like you ask the attributor, get me the attribute for value simplify for the first operand, which is the return value. And then that value, you just combine that with your current state. I'm not going to show that, but basically if you only do constant propagation here, you say, give me, is that a constant? If so, is it the same constant as I'm currently like holding? Then all is good. Otherwise, I'm done, I'm out. It's not a constant return. So, but all of it like works like through these recursive calls. And the trick about these recursive calls is the attributor will use them to determine the dependencies between your abstract attributes. So if this, whatever is returned here, if that changes in the future, it will trigger an update of this abstract attribute as well. So that is the way it knows what to update. So it doesn't have to update all the things all the time. Okay, so, sorry. I wanted to talk about a couple of other things. First is we added new attributes over the summer, which we did use in the attributor. And I think it's worth noting because like this is a stage where some people see this. So I wanted to briefly mention them. So we have no free. No free basically says a function will not free any allocated, like dynamically allocated memory. It will not call free, like transitively. That's what it says. Then we have no sync. A function will not synchronize with any other like running thread through any means, memory or like any volatile accesses to memory, atomic accesses to memory, or other means that might not go through memory. Like there is ways we have in IR that synchronize not through memory. So this is like if this attribute is set, you know there is no synchronization happening. If not, it might. Will return tells you that the function will actually return. Like if you call that function, the call will return. It does not mean the call will not throw an exception. It means it will not call exit, or it will not like have an endless loop or endless recursion or something. So it will come back to you either through an exception that goes through your call site, or it will actually just return. So if it is no unwind and will return, it will actually return to you. So it's orthogonal, but you can have both. And then finally, dereferenceable globally, which is a way to fix dereferenceable. I'm not sure if everyone is aware. We have the dereferenceable attribute, and the front end that puts them there and the optimizations that use it don't agree of what it means, which usually is a bad thing, and it is a bad thing. So like the consensus is to come out, like to add a new attribute Yes, here we go. Sorry about that. So we have dereferenceable globally, which means like it is, if ever said, the dereferenceable property will not get lost, while dereferenceable as it is right now will allow the dereferenceable property to get lost, which is basically what Clang thinks it means, and dereference globally is what some of the optimization think it means. So we will have two things for two different things, two different properties, and maybe you noticed no free and no sync are necessary to derive dereferenceable globally from dereferenceable. So all of that, like, it comes together. So like you need those properties. Now, we also have non-attribute deductions in the attributor. As I said, it's like a fixed point iteration framework. It allows you to do whatever. And you don't have to have attributes that you derive. What we, for example, have is liveness. We talked about that before, which is like always present, actually. You have to really opt out. And if you don't opt out, you get a lot of benefits. For example, you will only visit live and reachable instructions, which means SSA properties hold for everything. So you don't have to worry about like broken, unreachable code and all of the other nastinesses that can actually appear in unreachable code. And so liveness is nice. You get return values, so all the values that can be returned, even if it's not a single one, maybe all of them together have a certain property you're interested in. You can also get, they are categorized by where they're returned, so you could potentially use the control information at the point where they're returned to simplify or to utilize it. We have value simplify, which is, for example, constant propagation and constant folding. And we have heap to stack, which takes malloc and a free that is corresponding and always reached will return again. Like if everything in between will actually like terminate and it will reach that, or if the malloc pointer is not going to escape, it will like put it on the stack if it's small enough. And then we have pointer privatization, which is basically argument promotion, almost. Right now it's not that powerful, but once it's like all of it is in, it will be more powerful than argument promotion. And the idea is instead of passing things by reference or instructs, we unpack it and pass it as values, at least for the part of the passing, because we can analyze those values much better. Okay, now there's a couple of challenges, but I'm running out of time. So one of the things is when should we specialize, which basically means like conceptually you can think of it inline the call and outline it again, such that you get an internal version of that function. We can do that transparently. We can pretend we did it, and then afterwards see what would have been impacted, what would we have gained if we do it, and based on that information, we can do it or not. But coming up, we have all the information, but the heuristic is missing. Talking about heuristics, where do we seed values? Because right now, the attributor seed tries to deduce everything everywhere. But we don't have to. You can say, I'm only interested in alignments for loads inside of loops. And it will look at everything related that it needs to look at, not further. But you don't have to seed it everywhere. You seed it where you want it, and then it runs until it comes to a fixed point and only looks at the stuff that is important. We have a lot of things that low-hanging fruits to reduce overheads. We could use pool allocations and other things because we have a lot of small allocations, a lot of other, it wasn't designed to be really well designed right now. And then we have things that I'm not going to talk about. Evaluation, these are just numbers we have on our poster. So please come to our poster if you want to see how many of all pointers in total we can annotate with align, dereferenceable, how many more we can annotate than function attribute deduction right now, and a lot of other things. So please visit our poster tomorrow. We have all of that there. You also have the HTO, the header term optimization, the student research competition talk. So watch the video if you haven't seen it. And there's a poster on that where we show that a lot of the information we derive can be used to match LTO performance, which is great. And so there's a tutorial tomorrow in which we will, derive a new attribute, introduce a new attribute into LLVM, derive it into Attributor, and use it to improve alias analysis. All in that tutorial. If you're interested in that, come to the tutorial, come to the poster session, and thank you.
any questions, there's the microphone in the middle, or you can raise your hand and I will try to come to you with a microphone.
Does your heap to stack promotion work with other sources of memory allocation other than malloc? Like
right now,
garbage collectors or?
Right now, it looks like is malloc-like, which we could like extend to is new-like, and then from there on to anything that is reasonable. Like is malloc-like is already like a slight abstraction over how the call actually looks. As long as like we have two strategies to do heap to stack. As one is the pointer is never captured, does never escape, so moving it to stack will not hurt. And the other one is it will always be freed, whatever happens. And as long as like we can match, like argue what the free is, that strategy will work. And the other strategy should always work. So there is no limitation to it being malloc.
Thank you very much.
Yeah.
I missed something in your very first example when you were demonstrating the fixed point analysis for the alignment.
Yes.
How did you go from like getting fixed at 116 to going to 1616?
Oh, so at 116, you can run update everywhere and nothing will change anymore. Like 116 is what like now, and at that point, your assumed value is basically what you get. Like that is the correct value. So, and like what the attributor does internally, once it realizes something doesn't change anymore, and it cannot change anymore, it will just move the known value to the assumed value. Why? Because certain optimization and deductions depend on the known values, not only on the assumed values. So doing that early instead of late can have a benefit during the translation. But that is not pure fixed point analysis anymore. That is just like some things we add to make it better, whatever that means.
Hi. So how general is this fixed point iteration framework compared to like abstract interpretation by like Kuzo and Kuzo style? Or are they general enough or not?
You can do what, like, it should be general enough. It should not, like, there is no inherent limitation to it. So you can, like, mimic all of those, yes. It's more like an implementation thereof with a couple of, like, neat features that make it easier to use at the end of the day. But it doesn't really divert from the algorithms.
How does adding new abstract attributes affect scalability of the whole thing?
Sorry?
You said that you can add new abstract attributes and they can reference the other ones?
Yes.
So you can use the in-flight information?
Yes.
How does that affect the scalability of the whole thing?
That depends. Right now, you can have actually bad situations where like you get like cascading failures, like everything kind of, you build a big dependency chain and then one at the end fails, like it goes into like a pessimistic fixed point, like the valid state goes to 0 or whatever, and then iteration after iteration you have to invalidate information, like, and it will take forever because you have to go through the whole iteration process. We plan to introduce new kinds of dependencies that make it easier to like say, okay, if this one ever like loses its valid state, invalidate this whole chain of things. So at least that problem that this cascading failure goes away. And other than that, now it just depends on how many connections you make and how long. Like, it can take long, and the timeouts we have right now are based on iterations, like on whole system iterations, because that scales nicely with the program size. Double the program size, we're kind of allowed to use twice as much as like on time. But you can add other timeouts. And I don't have real good like results on telling you how it scales. Like so far, we had sometimes problems, real problems, but usually there were bugs in our implementation where we like return changed even if it didn't, or where we're just stupid in updating things. So we could have like bailed out earlier. And sometimes that happens, but I can't tell you more than that. Sorry.
So I'm curious, it seems like some of the attributes you're talking about have very small potential cardinalities. So like it's either synchronous or not, right?
Yes.
So that's a very small set to keep
Yes.
track of. Whereas other ones could have very large cardinalities, like when you start talking about doing like live value analysis or something.
Yes.
So do you have good infrastructure for representing the infinite sets, or is that sort of up to the attribute in each attribute in itself to sort of figure out how to represent that set efficiently, or how do you?
Right now, on that part, yes, we only offer good infrastructure and pre-built like abstract, like implementations of abstract states for integer states that you use decrementing, incrementing as bit sets or as booleans, like all of these simple ones. And then we have like 3 or 4 that have more complicated states. One of which is an optional value, which we could like generalize, which would be nice. But other than that, no, we don't offer like help, and the people are on their own. But we should try to come up with good classes of things. I'm not disagreeing. I see where you're going, and actually, we should do it for sure because it's hard to actually implement them correctly, and then you like run into problems later on. So I totally agree.
So I found it in some cases doing very heavy memoization of these kinds of attributes or classes works very well. So it might be good to be able to pull the memoization of that into the kind of base framework. It's sort of a trade-off on whether the cost of a pointer is bigger than the cost of the set that you're trying to keep track of.
I don't have any evaluation on that. We only have like the ones that we have that have complex states. We just have basically one implementation of them. I didn't play around. I didn't do much. We try to get like a bigger framework working to like show like why you need a framework and all of the other things. And now this is part of the tuning that we actually need to do. And I hope that people get interested in this and actually start to help, because like just like 2 students and me, it's a small set of people to work on this. I'm sorry.
Cool. Thanks.
Thank you.
We're running out of time. Let's do one final question.
Okay, so I'll keep it short. So I was just wondering, when you there is this dimension of context sensitivity.
Yes.
And I assume that in the states that you deal with, you are being context sensitive. Is that right?
Right now, we are actually not, because we can be, and we can easily turn the switch to be 1 level context sensitive. So you get like call site specific information about the callee. That will be very easy. There is nothing in there to allow you like call string, like call chain based optimization. We don't have the infrastructure to do that. Okay. But for one call site, like 1 level, that should be fairly easy to do. And we didn't do that because we just finished value simplification. And you only want to do that if you, like at the call operands have special properties, like let's say they are constants. Mm-hmm. Then you want to do that. And so you want to, like first we had to like get that in place, and now at the call site, we can look at the call operands, compare the results of like the value simplification to the generic result of the function argument. If it's better, we can just opt into keep the call site information instead just like importing whatever the function information is. Right now, we just import whatever the function information is in all these situations.
Okay.
But 1 level will be is already in planning. I don't know about more. If that is something people are interested in, we can add that.
Okay. Thank you.
All right, let's thank our speaker.